Hello everyone. Today we're going to talk about the central limit theorem. Okay. The central limit theorem tells us for all samples of size n greater than 30, the sampling distribution of x bar can be approximated by a normal distribution with the mean mu and standard deviation of sigma divided by the square root of n. So I wrote it in words and then I wrote it with the symbols below, or put it with the symbols below. But what we're saying here is if we have a big enough sample size, so if our sample is above 30, we can compute the sample mean. Remember, sample mean is x bar, and it can be approximated using our normal distribution. So this is really big because what it allows us to do is as long as our sample is big enough, we can assume that it can be approximated by a normal distribution, and then we can solve it like we were doing before. Let's look at these following two examples. In the first histogram, the original data is 1,000 Boston commute times. In the second histogram of 1,000 sample means where each of the 1,000 samples include 50 Boston commute times. All right. So we can see in the first one, we're going to have a non-normal distribution. So we're just looking at one piece. We just have one set of data, and we're trying to have the distribution. Instead, we have 1,000 sample means. So it's a little tricky with how we're saying means, but I'm taking 1,000 sample means and only computing the means here. So we have just one set in the first one, clearly not normal. But if I take a whole population and I'm taking 1,000 different samples, then it's going to normalize. All right. So let's look at a little chart here that explains what we're going to do to solve some of these problems. So what needs to be given first? We need a population with any distribution, and we need to know mu and standard deviation. So I kind of hinted at that last time. We need to know this mu and sigma. The second thing that needs to be given is we need a simple random sample. All of the same size n are selected from the population. So samples all have to be the same size n and are selected from the population. And then population has a normal distribution, or n can be greater than 30. We can compute the sample mean. So we'll see a little bit later on that if n is not greater than 30, it's okay. It still could be normally distributed, but we'll have to do a little bit more work to make sure everything's okay. And then below, we just see how we switch from population to sample. So our mean for the population, we write as mu. So now that we're using x bar instead of mu, we write it mu of x bar. So it's the mean of the sample. Same thing with standard deviation. It's the standard deviation of the sample. And then our formula for z-score gets a little bit trickier since we have doing it for the sample. So we have x bar minus mu divided by sigma divided by the square root of n. So our original population is not normally distributed and n is less than 30. The distribution of x bar cannot be approximated well by normal distributions, and we would have to use other methods. So we won't really focus on this. We'll normally have either n being greater than 30, or we'll just have it normally distributed to start with. So when we're solving problems, our first step is always going to be to check the requirements. When we are working with a mean from a sample, we want to verify that the normal distribution can be used by confirming that the original population has a normal distribution or the sample size is n greater than 30. So if n's bigger than 30, easy, we're done, we can keep going. If not, we have to do a little bit more work to make sure it's a normal distribution. Okay. Second thing we should consider, is this an individual value or mean from a sample? So this part's a little tricky here. So this kind of talk is a good way to think of these graphs below. The first one is just an individual value, and then the second one would be a mean from a sample. So an individual value, when working with just one value, we can use our normal z-test, x minus mu divided by sigma. If we have mean from a sample of values when working with a mean for some sample of n values, be sure to use the value of sigma divided by the square root of n for the standard deviation of the sample means. So use our new z-score formula. And normally in the question, it'll be pretty straightforward of when to know which one. If you're just given one individual value, it'll be for our bone density questions. We're just given a bone density more than or less than z equals something. Now, when we take a look at the wording of these upcoming questions, there's normally the word sample mean in there or something along those lines. So let's look at an example. Boeing 737 airline seats. American Airlines using Boeing 737 jets with 126 seats in the main cabin. In an attempt to create more room, an engineer is considering a reduction of the seat from 16.6 inches to 16 inches. Adult males have hip widths that are normally distributed with a mean of 14.3 inches and a standard deviation of 0.9 inches. We want to find the probability that a randomly selected adult male has a hip width greater than the seat width of 16 inches. We want to find the probability that 126 main cabin seats are all occupied by males with a mean hip width greater than the seat width of 16 inches. And then for the design of the aircraft seats, which is more relevant. So a little practicality here of just because we find some statistical number, we have to apply it to see if it makes sense. All right, let's look at approach one. Approach one, we are just given a singular value. I'm given this singular value. We want to find the probability that a randomly selected adult male has a hip width greater than 16 inches. So I have just an individual value, which is 16. I can plug that right in. 16 minus the mean of 14.3 divided by the standard deviation. We find our z-score. So this is our z. And then we use our chart. We use the chart for z equals 1.89. We see that we would have 0.9706. So go back and check this one, make sure we can read our chart and see that we'd get 0.9706. So then the probability would be 1 minus that, because we want to the right, we want bigger than. So it's a probability of about almost 3%, 2.94%. So that's one piece of data that we would have. If we use the second approach, let's go back to the question. We want to find the probability that 126 main cabin seats are occupied by males with a mean. So mean is the big important part here, is to know that we have to use our other equation. So we're dealing with a sample mean, hip width greater than 16 inches. So the difference here is we're given a mean. First one, individual value, here, mean. Okay. So we know that our mean from the question is still 14.3. We just changed the notation a little bit. So nothing changes there. Standard deviation of x bar is the same thing as sigma over the square root of n. So that's the denominator of our new z equation. So sometimes people will just plug it all in at once, or you could find the standard deviation separately. Doesn't really make a difference. So we know our standard deviation is 0.9, but now we have to plug in that 126 here as well. So that's the only difference here. Since we're dealing with a mean, we divide by the square root of that number, and we'll get a standard deviation of 0.1. And note the standard deviation is a lot lower because we're dealing with a mean, not just one value. So the mean shouldn't change as much. And then we can go ahead and plug it into our new equation. So we have x bar minus mu of x. Still using the number 16 minus 14.3, we see that the only difference is this standard deviation at the bottom because we're dividing by the square root of n. Then we get a z-score value of 17. So now we have to think about this. Our first part of the question, we get about 3%. So let's go back to look what the question was asking. So the probability that random selected adult male has a hip width greater than the seat of 16 inches is 3%. So thinking about that, that means every time you board a flight, 3% of adult males have a chance of having a hip width greater than the proposed seat. So that sounds like a big deal. Since if every time there's a 3% chance that someone's not going to fit in the seat, that's a problem for every single flight if this is a problem that you occur all the time. Second piece tells us the mean. The mean may not be as helpful. So the mean here we see is the probability is 0.001%. So the means might not have a significant value here, which it's a very small chance that the mean is less than 16 inches. But just one person is all that matters if we're dealing with a flight. So it's highly unlikely that 126 males will have a mean hip width greater than 16 inches. We don't care what the mean is. We just need, if one specific person is bigger than 16 inches, it doesn't matter whatsoever what the mean is. It's just that person is bigger than 16 inches, so they're not going to fit on the flight. So we can see the first part is more relevant. Individual seats occupied by individual passengers. So individual value for individual passengers would make more sense, not a group of passengers. If the mean was bigger than 16 inches, sorry, the mean was a crazy number, or the mean had a crazy high probability, that'd be a really big problem. But it's not likely because it's the mean, it's not one individual value. Even though 3% seems small, however, so yes, 3% is small, we found from our individual value, that would be quite inconvenient if 3 people on every flight need special arrangements. Or probably a little less than that, because this was for, I believe, just adult male. But still, every 120 or so people, males that fly, 3 of them don't fit. And that's just including males. So that's probably a problem. 3 people on every flight, probably not the best way to engineer these flights. So here we can see the difference of when we want to use an individual value, when we want to use a mean. Next time, we're going to start talking about assessing normality. Have a great day, everyone.